I'm sitting at a table today, mainly because I want to show things in 3 dimensions. And when you try to draw on a flat surface, when I use my little drawing board, it doesn't work too well. So far, all of the problems that we have worked with in quantum mechanics, the free particle, the particle in a box, the harmonic oscillator, they all could be done in 1 dimension. But when I went to the rigid rotor, the whole thing was rotating around. So it became necessary to use what's called spherical coordinates. Spherical coordinates. So what are we used to? We're used to rectangular coordinates. So here's one of my axes. Here's the x-axis. And here's the y-axis. Let me make it look good on the screen here. There's the y-axis. So you can see that, well, let's see, which way works best? I guess that works best. Here's the x-axis, or could be the x-axis, and here's the y-axis. So that gives us what? 2 dimensions, flat surface, no problem. Now, what if I did the flat surface in spherical coordinates? Take one of these axes away, and I'm going to make this my radius. So this could be one axis. And then what I'm going to do is wherever this axis turns, I can express that with an angle. And what I'm going to do is the traditional way is when this thing turns around, it's going to form an angle phi. In the past, I've used the Greek letter phi, P-H-I, but it's actually pronounced phi, and I'm going to rotate this thing around. So this would be a flat surface in spherical, well, it wouldn't be spherical, it would be circular coordinates because it's a flat surface. Now, what happens if we go to 3 dimensions? Okay, 3 dimensions. Here's the x-axis. Here's the y-axis. And here's the z-axis. So I've got x-axis, y-axis, and the z-axis. If I give a x, a y, and a z, then I've got 3-dimensional coordinates. And if you remember, or if you don't remember, what we've done is take the second derivative of things when we were in the Hamiltonian or Schrodinger's equation. So we have to take the second derivative of things that are rectangular coordinates or the second derivative of spherical coordinates. Now it happens that the model of the atom, you're talking about a radius and things spinning around, so spherical coordinates work a lot better for that. So how do I represent that with with 3 quantities? Get rid of those axes. And I'm going to have one axis at the origin. And that axis in 2 dimensions is going to be like this. The length of the radius and the angle of rotation. So this would be the r and the phi. And then what happens to the 3rd dimension? Well, you take that same single axis and give it an angle phi and an angle theta. So you've got a theta angle, a phi angle, and a length r. And those are the 3 spherical coordinates. 3 dimensions, 3 coordinates. Now let's get down to nuts and bolts and put this stuff on paper and try to figure out what's going on. Here are the 3 spherical coordinates that I mentioned. R is the radius. That's pretty easy. It can go around and around and up and down. And the round and around, if you want to think about it that way, in the x-axis, in the xy plane, is r and phi. Between r and phi, we can represent the two dimensions. Notice there's no z over here. And in the xy plane, z would be 0. So it would just be, this would be two dimensions, r and phi. Now, if we go to the third dimension, then we have to get a little more complicated in that what we're doing is we're looking at, oh, well, maybe you go back here to this thing. Arctan, what in the heck is this all about? Well, if you think about it, if you take the angle whose tangent is y over x, that's going to give us the phi dimension. Phi dimension. And if you think of if y is 0, then what's the tangent of 0? Well, the tangent of 0 is 0. And the tangent of x is 90 degrees. When tangent of 1 is when y and x is equal, and that angle would be 45 degrees. I hope that's fairly clear. Now, if we go to the arctangent, then we have to use this value. Here's the z value, which that makes sense because here we're lifting out of the xy plane. X squared plus y squared value is going to give us the numerator of this tangent, and z is going to be this. Now, what would x squared plus y squared, if both x and y were 0? That would be fully z, and then the angle would be 0. 0 over 0, and z could be anything else but 0. Then if we look at the other thing, the infinite value, is if z is 0, then that just means we're at an angle of 90 degrees. And if you take negative and positive values of this thing, you can get to all the different other positions that you can come up with. Now, I hope that made a little bit of sense, but now we want to go from this form. Notice we're relating these three to the x and y coordinates, which we need to explain that. Why do we have to include x, y, and z? Why can't we just use these three coordinates all by themselves? Let's look at this from the other side of the tracks here. X, Y, and Z, and then here we took R, theta, phi. Now we're going to take X, Y, and Z and put it in terms of theta and phi. If the sign is 0 in either case, that means that the angle or the radial thing is directly in the z-axis, and so there's no x or y component. Now, if these cosine phi and sine of phi will be represented the x and y, just kind of like the unit circle. And r cosine theta, notice here r sine theta, if it's 0, here r cosine theta at 0 is 1. So that means if it's all z-axis, here that shows up that way. I hope that made some sense. Now, I'm going to get a little involved here, and it might not make some sense, but here we go. We're going to define I, j, and k as unit vectors, and here I've got the three-dimensional y, x, and z dimensions. So if I look at this, I, j, and k, then I can represent the position vector, which I have as this green thing out here, and that's going to equal to x times the I dimension, y times the j vector, and z is the magnitude of the k vector. Then I'm going to plug in for x, r sine theta cosine phi, and r sine theta sine phi, and then finally r cosine theta for the z. Hopefully all that makes sense because we're going to build on this information. Here's the position vector that we just developed, and this is the combination of radius and theta and phi values that give us the x coordinate along, and we're just using this I, J, K so we don't get mixed up between rectangular and spherical coordinates. And the same thing is done here for the J or the Y coordinate part of this and the K, which is the Z coordinate. Now, what's the whole point of this? What we want to do is take second derivatives. That's where we're headed, because if you remember in the Hamiltonian, we took the second derivative of x for that big portion, the really important portion of the time independent portion of the Schrodinger equation. So let's get started here with taking some derivatives, not of x, y, or z specifically, but we're going to see what s is with respect to r. To take the derivative of s with respect to r, we take the derivative of this quantity plus the derivative of this quantity plus the derivative of the k vector quantity. So let's see if we can add those together. Derivative of s, or derivative of this quantity with respect to r, well, the derivative of r with respect to r is just 1. So really what's going to happen is, for this line here, it's just going to be sine theta, cosine theta, sine theta, and cosine theta. Now, this one was really easy. So let's look at what happens if we do a derivative with respect to theta. So we're going to focus on those trig functions that are theta. Now, in order to do derivatives of trig functions, we're pretty easy on this thing. The derivative of the sine is the cosine. The derivative of the cosine is the sine, or negative sine. So let me just apply this and see if it makes sense to you. Derivative of this position vector with respect to theta is going to be r. Can't forget about the r. The r doesn't change with theta. So we put in here cosine theta. And the cosine phi doesn't change because we're only looking at the theta angle, or the phi. I keep saying phi, but it's phi. Phi, phi, pho, phum. Let me get this little thing in here. And for the next one, the r comes along for the ride. Now, it's also sine here, so we get another cosine theta. And the sine phi doesn't change. Sine phi j vector. Notice I'm going to put a minus sign here because the derivative of the cosine is minus sine. So that's going to be minus r sine theta Now, one thing to notice here on this line is that we have a common factor that we can factor out of all this. And in order to emphasize that, I'm going to underline the common factor of r in each one of these. Now, for this final line, we're going to focus on things that have the phi angle in them. And if you look at this top line, the phi angle is going to be in the cosine phi. So that's going to come out to be a minus sign. So I'm going to go ahead and put a minus in front of this thing and make that as a minus r. The sine theta doesn't change. And the cosine changed to a sine because we put the minus sign out front there. And all that is a coefficient of this I thing here. Now for the second term, we're going to do a derivative of sine phi. So the r sine doesn't change. That's going to be plus r sine theta. And that's going to be cosine phi. Let's figure out what all this stuff I just slapped up on the screen in front of you. Well, we finished this one and saw that there was a common factor of r sine theta, common factor of r, and no common factor here. So what I'm changed is, rather than s, I have broken these things down into a name which I call r operator. That means I'm taking the first derivative, or I've taken the first derivative of r with respect to r. First derivative of the position with respect to r. All this stuff is just position. And down here, I've taken the first derivative with respect to theta. Note that the r's are not in there, but we can't forget about them. We need to still consider those r constants later on. And down here, the phi vector, or the phi operator, it's not a vector. Notice I put a little hat symbol on here rather than had arrows over here for vectors. So the phi, or up here for the s, the phi is going to be an operator where the r sine theta constant is canceled out. This page is focusing only on the r operator. Notice everything is r operator in the numerator of this differential thing, partial differential. So in this first one, r hat, or r operator, there are no r values in here. So the change in r is simply 0. Now that does result in a vector. So you got the I, the j, the k, so that's really a 0 vector. Now the partial of r, notice we're taking the partial of an operator that's already the first derivative. So that's cosine theta, cosine phi, which is let's walk through that one first. Sine theta becomes cosine theta. That makes sense. Over here, sine theta becomes cosine theta. These two phi values don't change. And then over here, we've got a cosine which becomes a negative sine. It's all kind of fitting together if you can keep track of the trig functions and their derivatives. Over here, I drew theta, and down here, I said, over here, I put theta operator. Theta operator. Now, why would I do that? This is to help us understand why I've got the theta operator in here. Just kind of hold this in your head. Cosine, 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 sine, minus sine. So I can just say the partial of r operator with respect to theta is just theta. So you could scratch out all this and put just theta there. On this one, if you factor out sine theta out of both of these, you're right back to the phi operator. In like manner, here's the theta operator, and we're going to take a partial with respect to theta of the theta operator. Now let's see why I've got 0 here. Well, that's with respect to r. There's no r in here, so that just becomes 0. Remember, the r was canceled out, or I'm sorry, the r was factored out of this thing. Now, if we go down here to theta with respect to theta, we come up with minus sine theta cosine phi minus sine theta sine phi minus cosine theta. That is negative. If you pull the negative out of there, that's the same as the r operator. Notice there's no r because partial of r with respect to r is just 1. And finally, down here, partial of theta with respect to phi. Let's look at this. A minus cosine sine plus cosine. Okay, you just pull the cosine out of cosine theta out of there, and you're right back to the phi operator. Now, you might want to go back and review some of these video segments here so that you can keep track of what's going on. And now finally, here's good old phi operator is minus sine plus cosine. If we take the partial of phi with respect to r, 0, no r's there. If we take the partial of phi operator with respect to theta, 0, no operators there. And if we take the partial of phi with respect to phi, then we get a switch around here. Minus sine becomes cosine, and cosine becomes minus sine. So we've covered a lot here. We found the partial of each of the operators with respect to each of the other things. And this is going to be important when we take the second derivative, which we're going to give that a special name. We're going to give that second derivative of this three-dimensional thing the nabla symbol, which is the upside down triangle for delta. And we're going to use and put a number 2 out there, and let's see what that looks like. Here's the first derivative thing. I'm going to use a new symbol called a nabla or a del, and this is going to be we're going to take the first derivative of the r things. Notice the difference between the r operator and the theta operator and the phi operator. Each one of these has a constant below it except for r. Well, we couldn't, and the r operator, we couldn't factor out any constant. So that's going to be this relationship, but we have to hold all this junk in our heads when we go forward with this. So let's look at the first part of this. The r, remember we want to take the second derivative. This is getting really complicated. And when I went through this the first time, I got really confused by it. So this is going to take us some time. Let's see if you can look at this triangle thing, which is a upside down triangle, I should say, which is this, let's call it a del instead of a nabla. That's kind of an oddball thing. But I'm going to take this quantity here, which is on our way to finding the second derivative. We're going to look at this and the r operator times the partial with respect to r times this nabla operator. Now, if we look at this, that's going to be r times r operator. And when we take the dot product of the same vectors, it just comes up with 1. So trust me on this one, it does come up with 1. If you want to go back, you can look at dot operators and try to work that out for yourself. And then notice that this partial here times this partial simply becomes a second derivative of r. Oh, here we go, second derivative of r. That's just what we wanted. Okay, now I'm going to take the r operator times the partial with respect to r of this second term. So what happens next? Well, I take this was the first term, so let me take the second term. Notice the 1 over r comes out front because we factored that out. Now the r operator dot the delta, not delta, but the theta operator, those just become 0. So when we're analyzing stuff, that's nice. That just goes to 0. The r operator, still got the r over here. The partial of theta with respect to r is going to be 0, so that term drops out. So we've got a 0, we've got a 0, we've got a 0. Boy, this is getting really simple. And this last line here, 1 over r sine. Now, why is it 1 over r sine? Because we're talking about the phi part of this. Here's the phi, there's the phi, everywhere's a phi. And we're going through this and we've got zeros, 0, 0. So what's the net result of all of this stuff? I think if you look at this, everything is 0 except for where I've circled the whole thing. So we had to go through a little bit of trouble there, but that's a good result. Now, are we done? No, we're not done, because we have to take this whole thing, we have to consider what's going on with the theta operator and the phi operator. Let's step back a minute, and I'm going to prove the dot operators rather than just saying, oh, it's equal to 1. If you notice there's a little algebra involved. Here's the I component of the r vector squared, the j component of the r factor squared, and the k factor component squared. If you look at this, you can factor out a sine squared out of both of these terms. That gives us cosine squared plus sine squared theta. That is equal to 1. And then if that's 1, then we have sine squared plus cosine squared. That's equal to 1. Let's try this one. Here's the r component of the I vector. Here's the theta component of that thing multiplied together. And the same thing is done here for the I component and the j component and the j component here. And here's the k component. One is cosine theta for the r, sine theta for the theta operator. Now, if you notice, we can multiply these things out and pull a sine theta, cosine theta out of each one of these. And that's going to leave us with cosine squared phi. And down here, that'll leave us with a sine squared phi. Well, that equals 1. So you think, oh, it's going to be 1. No, because if you take sine theta cosine theta minus cosine theta sine theta, that's just going to equal 0. Okay, we're almost done here. R dot phi, this will give us the pattern here, and I think you can live with some of these others. R dot phi, here's the R component, here's the phi component, Remember, phi just has a couple is very simple terms, and the here's the r component and the phi component, and the last component has a uh, 0 for the r component. So that thing just goes away. That term goes away. And what are we left with? Sine theta, cosine phi, sine theta, cosine phi, sine phi, just by jiggling the things around. And one's a negative, one's a positive. There we go to 0. Finally, here's all of them. R dot R is 1, R dot theta is 0, r dot phi is 0, uh, theta dot theta equals 1, theta dot phi equals 0, and phi dot phi equals 1. This proves everything out so that there's no question in your mind how we got some of these things. Let's look at the first step in determining what the Laplacian is. Here's the R operator, here's the delta operator and the phi operator, and we've already determined that this n sub r is equal to 1. This n sub theta is equal to r down here in the denominator, and this is equal to r sine. This screen should look familiar. This is the item that we've already worked through, and then it just comes out to be second derivative with respect to r squared because of all these other zeros that occur. So let's go on to this number 2, where we're doing the same thing, same kind of operation, but we're using theta. Some examination here. The one thing we proved was that we do the delta operator dot the r operator, that's a 0. So it takes care of this term. This one's a little tricky. Delta r operator with respect to the delta operator is with respect to delta of the r operator just comes out to be delta. So we've got delta and delta, which equals 1. So what's left here is 1 over r times the partial with respect to r. This one, 1 over r squared. Let's see, where did the 1 over r squared come from? Well, we've got two deltas. If we have two deltas, that means we've got two 1 over r's. So that's going to give me a 1 right there and a 1 over squared there. And what's left is a second partial with respect to delta squared. All these others have some kind of factors that make them 0. And you can stare at this screen, pause the video, and go over there and prove to yourself that these zeros really are zeros. On to number 3. This is the phi stuff that's going on here. Okay, it's pretty easy to believe that phi dot r is 0. We proved that before. And let's see what's going on here. Let's see, if apparently nothing gets canceled out here. So that's going to give us, well, the sine theta cancels out. And we've got a, sine times theta, which is what happens when you take the derivative of r with respect to phi. That gives you sine phi times phi. So that's where the sine phi, we get rid of that. And then that gives us phi times phi, which is 1. So 1 over r times the partial with respect to r. And let's see, are there any other terms? Those turn to 0. That turns to 0. Let's see what happens down here. Oh, how do we get a tangent out of this? Well, let's kind of figure that out, see if that makes sense. We've got phi, which is r sine theta, which is the constant. That's the constant down here. And then we've got cosine theta, dot phi, and the phi up here becomes phi times phi, which is 1. And let's see what happens. All this nonsense turns into stuff, and we should end up with 1 over r squared. And why do we get a tangent? Why do we get a tangent? That seems like that's kind of confusing that we get a tangent. Okay, a tangent in the denominator because we had cosine over sine, which is the cotangent, but you bring it down into the denominator, then you get a tangent. So that makes some sense there. Then we have phi times phi, which gives me 1. I've got the r sine squared in the denominator, and then the second partial of phi with respect to phi, which is my desired second derivative things that's going on here. Okay, here's what we end up with. These are the results that we got from those 3 other screens. This was the we're taking this quantity against this first setup there. Anyway, all these 3 things come together to give us this as a result. Let's see if we can figure out what the further simplification is of this whole thing. Notice that we have a 1 over r partial with respect to r. We've got 2 of those. So here we've got a 2 there. And let's see, what else is going on here? That still stays the same. That stayed the same. And that stayed the same. So the only difference was we combined this green 1 over r and this red 1 over r partial with respect to r into one piece there. For this final setup, to go from this step to this step is going to take some tricks. If you want to look at this screen, copy it down, and then try to figure out how you get from this step to this step, that would be a good challenge. I'm not up to it right now. To wrap this up, I'm exhausted with that math, as you might be also. I made some mistakes. I was calling theta delta in a bunch of cases, and I sometimes mispronounce phi as phi. So I'm noticing those things are not quite the greatest. This is not in my In Search of a Quark series because it's really math required outside of the stream of consciousness that we were trying to get to. So that's where I'm ending this video.